Was there any particular part you got stuck on?
The reset.
What did you do for resetting?
You know how you use different variable y? Yeah, I'm still not sure, like how to use that.
For which one? Part C? Is that the one you're doing?
Yeah, part C.
Did you do part B?
Yeah, I think so.
What did you get? Direction. Change.
Forward reaction.
Forward reaction?
Yeah.
Why didn't you just try to solve it off that? What was the ice table you got for 38?
38. Well, we always look, these tricks are just tricks in addition to all the other mathematical tricks that you use, right? And so what you should do is you should look for standard algebraic trick that you can use to solve this problem. So you said the forward direction. What were the concentrations that you got here?
The first, it was 0.029 molar.
Is that just a two sig figs? How many sig figs are you allowed?
3.
3, so
Yeah.
we need more sig figs. What is it?
I only wrote down 2.
Was it 290?
Yeah.
290?
290.
All right.
Yeah.
Just leave it.
Yes,
CO2?
0.0524.
0.0524.
Yeah.
Give me one more digit.
Zero.
0. And then CF4?
0.0148.
0. All right. You said you calculated Q and it goes forward direction? Forward. So minus 2x plus x plus x. And then at equilibrium, what do you have? 0.02900 minus 2x. 0.05240 plus x. 0.01480 plus x. Is that right? And then Kc. This Kc tells you what about this equilibrium? This 2. And so Kc of 2 tells you neither side is really biased.
Yeah.
Right? And so maybe it's going to be like this. I mean, if we were to reset this, it really doesn't matter which side you set it on. But let's see if we don't reset it, what happens here. So this is going to be the CO2 concentration times the CF4 concentration over the COF2 concentration squared. 0.05240 plus x times 0.01480 plus x over 0.02900 minus 2x quantity squared. So we have this problem. Will the simplifying assumption work in this particular problem?
No, because all the x's are canceled.
Yeah, all the x's would drop out, so we can't use the simplifying assumption. So we could try resetting it and then see.
Yeah, sorry. And then I was confused on like the y and stuff because in the notes sometimes you subtract so like for the 2COF2 you did minus 2x molars, right? And then sometimes in the notes you do like plus 2y, and then on the other side you subtract x molars.
It depends on which side you want to reset it. If you want to reset it to the left or reset it to the right. And so which way do you want to reset it to? Left or right?
Forward, I guess. Right.
If we reset it to the right? Try that.
You guys, yeah.
Okay. Alternatively, we could just multiply that out. That's still only quadratic, and so it's quadratic we should be able to solve, right? And so we don't really have to resort to reset here. I mean, it's a lot of work to multiply it out, but you can do it. You know, it's not that hard.
Yeah, that's true.
Right? And so, in this particular problem, you don't really have to reset, but reset might save you a little bit, or might save you a lot, depends. And so, if we reset this where? Which way? Right?
Yeah.
Reset? Okay. And so what we're going to do is we're going to just try resetting it then. And that's going to get rid of that. And so let's reset this. So we're going to get, if we reset it forward, then we're going to lose all. I mean, there's no limiting reactant here. So this is going to be our new initial condition. So we're going to be down to 0 molar. And so what do you call that? Minus 2y plus 2y. What do you want to call it?
Minus 2y.
Yeah, minus 2y. And we know that 2y has got to be 0.290. That means y is, 2y is that, then y is going to be half of that, which would be what? 0.0145. So this is going to be plus 0.0145, and this will be plus 0.0145. And so this is going to give us a point, this is going to be 9660, 0.0669 molar here. And this is going to be 13920, 0.0293 molar here. All right, now which direction is the change going to go? Yeah, it's going to go to the left. So this is going to be plus 2x minus x minus x. And so at equilibrium, I'm going to have 2x molar, 0.0669 minus x molar, and 0.0293 minus x molar. I'll drop the 0 there so we can make difference. And so this is going to give us a new K expression here. And maybe this is easier, maybe it's not. 0.0669 minus x, 0.0293 minus x, divided by 2x. We could try the simplifying assumption of 2x quantity squared. Should we just go ahead and try it and see if it works? Yeah, it's worth a try just to see. If we use the SA, then we're going to say that x is going to be smaller than 0.0293. So x is smaller than 0.0293. Then that's going to give us this. It's going to give us 0.0669 times 0.0293 divided by 4x squared. And then solve for x here.
Wait, for the simplifying assumption, you said x is smaller than 0.0293 because
Yeah.
that's the limited.
Well, this is the smaller number.
So you'll go with the smaller number.
Yeah, because if x is smaller than point.
Yeah, it might also be bigger than.
Right.
Other two.
Right.
Okay.
Right. Did somebody have x?
I got 0.01565.
Like 0.01565.
Yeah.
All right, then we have to justify it by calculating the percent change. The percent change is going to be 0.01565 divided by 0.0293 times 100%. And it looks like it's about 50% change. About 50% change is not valid, right? And so the simplifying assumption failed. And so what that means is we have to do the quadratic here for successive approximations. Now, was it worth resetting? There's another strategy to resetting. When we reset, we always end up with a zero somewhere, sometimes multiple zeros. So each zero we end up with in the initial conditions saves us one binomial, one fewer binomial that we have to multiply. So was resetting worth it? I think it was worth it because compare the two. Which one will take you less time to solve? The top one or the bottom one? The one I X'd out here or this one, the green one? Yeah, the green one's going to take you about, I would say, like 5 minutes less time, don't you think? And so it's probably worth doing the reset, which didn't take you an extra 5 minutes to do. As far as the strategy goes, in this case, it wasn't heavily biased towards one way or the other, so it would have been okay to reset it either way, to the left or to the right. It doesn't really matter in this particular instance. All right. Were there other questions?
So the resetting, you have, say, like if the KC was like 2.00 times 10 to the 6, then you would reset it towards the left.
To 10 to the positive 6?
Yeah, positive 6.
Well, ask, if the K value was 2.0 times 10 to the positive 6, would you reset it right or would you reset it left? Just a quick survey. Would you reset it right or to the left? If the K value, let's say we had a K value of 2.00 times 10 to the positive 6. Do we want to reset it to the right or do we want to reset it to the left? To the right or to the left? Where are most of the atoms? On the right side or the left side? Right. On the right side. So you want to push all the atoms to the right side. It's like the water. If most of the water is on the right side, push it to the right side. So this is reset to the right. If this was 10 to the negative 6, then most of the atoms are on the left side, so you reset it to the left side. All right, if there are no other questions, we're going to continue with chapter 16. In chapter 16, we're going to be dealing with two types of mixtures. There's going to be acid and water, and then the base and water. I call this multiple equilibria. The multiple equilibria is the acid. You know, an example would be HCl. If we have HCl, the first equilibrium, HCl is a strong acid. Are there any bases around that HCl can react with? Yeah, it's tricky. The base is actually water. And so if we have HCl and water, then what happens is we'll have hydrolysis or ionization. We'll end up with hydronium chloride. This is called Ka. A stands for acid hydrolysis or ionization, acid ionization. Kas are sometimes called the acid ionization constant. But we like to do hydrolysis like this, HCl X water. Kas are very common. The acid hydrolysis constants are usually found on the table. And so let's take a look at the table up here in the room. Let's see it over here. If we go to HCl, which is here, we see the Ka. This is written differently. This is written as an ionization. But you have to keep in mind that this ionization reaction and the hydrolysis reaction are the same. And this is just the shorthand way of representing it, because H plus just consists of a proton, is not stable in water. And, what's much more stable is hydronium. And so this is what we see. And so the Ka expression is going to look the same. For example, for HCl, the Ka expression will be the hydronium ion concentration times the chloride ion concentration divided by the HCl molecule concentration. Water does not appear in this because water is a pure liquid. Its activity is 1, so it's out. So if you look at the K expression, it's the same as this, up here. And it would be the concentration of the ions, so the ion product, divided by the concentration of the molecule, the acid itself of the species. So there's numbers here you can see, except for these. The strong acids, you look, HCl has a Ka value that's very large. This Ka is just the same thing as a Kc value. And so this is Kc. And it's literally very large. When you see very large, then we can assume complete reaction. If there was really complete reaction where the product goes is formed completely and the reactant is consumed completely, then the reactant concentration should go to 0. So if we really had complete reaction, then K should be infinity or approach infinity, right? Because the reactants go to 0, that means the ratio goes to infinity. The actual value for this k is known, and it's nowhere near infinity. Yeah. But to make our calculations simpler, and it doesn't make a huge difference because essentially it goes to completion, we'll leave it as very large. So this is one equilibrium, and then we have another equilibrium, and that is, the water equilibrium, H2O liquid plus H2O liquid. This goes to hydronium plus hydroxide, and this is KW. Water hydrolysis, water ionization. So we have these two equilibria going on, and we did a problem yesterday, or not yesterday, last week, showing how the addition of HCl can perturb water's equilibrium by the Le Chatelier's effect. But what we're going to do is we're going to do it differently now. All the problems in chapter 16, for multiple equilibria, what we do is we try to solve them stepwise. Starting with the largest k. For multiple equilibria, if they are interdependent. If they are independent, then we treat them as separate problems. If they are independent, then treat as separate problems. These two equilibria are interdependent because they have a common species. When you look at Ka and Kw, what is the common species that they share? Well, hydronium, and water, I should say, but water is always there. So in this case, hydronium would be the unique species. And so in this case, we'll try to solve them. If there's nothing connecting these two equilibria, let's say, the first equilibrium involved a series of species, the second equilibrium involved a series of species, and none of them were related or the same, then we could treat those as two separate problems and solve it as two separate problems because they don't influence or impact one another at all. But in this case, since hydronium is there in both of these, then we try to do this stepwise. And I'll talk about what stepwise is in a minute. But if stepwise fails, then we have to do this simultaneously, which is harder. If stepwise fails, then you must use simultaneous. I'll talk about how stepwise can fail. So the thinking behind this is this. The simultaneous method works for all multiple equilibria. In fact, all multiple equilibria should be solved simultaneously. That works. This would be like saying, all gas calculations should be done with the van der Waals equation, something like that. Because it's always going to work, right, the van der Waals equation, whether it's close to ideal or far from it. But the problem with using the van der Waals is it's more work. Right? Or this is like saying all bonds should be described using molecular orbital theory. All bonds should be described using molecular, which it's true, all bonds should be, because that's what describes a bond, but it's difficult. Okay? And so what we'll do is we'll just use valence bond theory until it fails, and then go to molecular orbital theory. Like, for example, O2. You know, O2 valence bond theory fails, and therefore we go to molecular orbital theory. Why? Because valence bond theory is just so much easier. And so same thing here. We should solve all multiple equilibria simultaneously, but it's too much work, too difficult. And so if we could solve it using the stepwise procedure, we will save ourselves a lot of work. So let me show you a typical setup for chapter 16. In fact, all the problems we're going to be doing like this. So it's just a redo of the previous problem we did. So the example is 0.100 molar HCl. I have the solution of 0.100 molar HCl, and I want to see what's happening in solution. You know, there are two things that we usually get from here that we want. You know, one thing is we want the inventory. You know, what are the species present in solution, and what is their concentration? The other thing we're typically interested in is pH. You know, what is the pH in this solution? So let's talk about the, this is multiple equilibria. There are two equilibria occurring here. You know, the multiple equilibria, we have Ka and Kw. You know, Ka for HCl, Kw. When we have multiple equilibria, first we're going to try to solve it stepwise. And hopefully it doesn't fail. We get a reasonable answer. But if it does fail, then we'll have to fall back on simultaneous. So starting off with stepwise, we start off with the larger K. Now Ka is very large. Kw is 1.0 times 10 to the minus 14. So we're going to start off with Ka, very large. So starting off with Ka, we're going to have HCl, you know, Ka is acid hydrolysis, so acid plus water. This is going to yield hydronium and chloride. Now, I already know that Ka for HCl is very large. Okay, we need to memorize this because all strong acids are going to have very large Kas. Not just strong acids, but strong bases. There's an equivalent term called Kb, which is base hydrolysis. Kb is going to be very large. Even soluble salts. And so this is pretty much, when we see a Ka that's very large, or a K value that's very large, literally, then we're going to assume something. What do we assume? We assume complete reaction. So if we assume complete reaction, then initially we might start off with 0.100 molar of the molecules. We're going to say none of them have ionized, or none of them have hydrolyzed yet. Water is a pure liquid, so we'll just omit that out of there. And what that means is if we have complete reaction, we're going to be left with no molecules and all ions. And so it's completely ionized or hydrolyzed. As we'd expect, you know, strong electrolytes should hydrolyze or ionize completely. Okay, this is what we call step one. Okay, now we move on to step two. Step two is going to be water. And autoionization. So we have H2O liquid plus H2O liquid. This is going to give us hydronium plus hydroxide. This is Kw here. Now, initially, we solved this before. We know what the hydronium and the hydroxide concentrations are in water. What are the hydronium and hydroxide concentrations in water? 10 to the minus 7 molar and 10 to the minus 7 molar, right? But we don't want to do this via Le Chatelier's. The way we're going to do this is this. Sorry, I'm going to have initial from water. We're going to reset it. And so even, yeah, this is 10 to the minus 7, this is 10 to the minus 7 in water. I'm going to reset all of it to the left. It's going to increase the amount of water in there. And so I'll start it from 0 and 0. So we're assuming no water molecules have collided. That's the initial from the H2O. And then I'm going to go initial from the HCl. The initial from the HCl is this. We're going to take this amount of hydronium and bring it down here. And so here I'm going to have my hydronium, and that's going to yield 0 hydroxide. And so now the total initial conditions will be 0 from the water, 0.100 from the HCl gives me 0.100, and 0 gives me 0. And so the water has not been allowed to react yet, you know, and this is just resetting it artificially. Now there's going to be a change in equilibrium. Now, we have to watch out. The solutions manual has error. Not just once, I think they do this twice. The solution manual contains errors. And so whoever did this problem did something very strange. What they did was they said, okay, I know how much water, when water collides with water, it should produce, can you guys see this? 1.0 plus 1.0 times 10 to the minus 7 molar plus 1.0 times 10 to the minus 7 molar, right? You know, when water collides with water, it produces 10 to the minus 7 molar hydronium and hydroxide. And then we just add them up. We add them up, so this would be whatever that comes out to. But there's a problem with this, and what is that problem? And so what we're going to end up with here is a 0.100. Now I need 6 zeros, so 1, 2, 3, 4, 5, 6, and 1 molar, and 1.0 times 10 to the minus 7 molar. What is the problem with this? The problem with this is this. This is like a Le Chatelier's perturbation. We were at equilibrium. This is the equilibrium condition for water. 1.0 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar. If we increase the hydronium, now we increase the hydronium dramatically. Le Chatelier's principle says we need to shift it left, but they're coming up with these equilibrium concentrations. These equilibrium concentrations don't satisfy K. If you do the K check, what does your K come out to? If I did a K check right now, it would be 10 to the minus 1 times 10 to the minus 7 gives you 10 to the minus 8. Is 10 to the minus 8 anywhere near 10 to the minus 14? It's so far off. I don't understand how the book got this answer. This is their answer. And it can't be right. The other way of thinking about this is like this. This is the amount of hydronium and hydroxide we generate if there was 0 and 0 initial. And so this would be like, you know, these are your deer and antelope roaming the plains of Africa with no predator around. But if there's lots, there's lots of predator, like 100 lions out, are you going to generate it? No, the population is not going to grow as big as it normally would. And so this population here cannot gut this big. In fact, X has to be much smaller than 10 to the minus 7. So this is wrong. And so let's go ahead and set it up again over here. The initial total is 0.100 molar for the hydronium and 0 molar for the hydroxide. Now the change here is, now I'm going to let the waters react. You know, this is all artificial, but this makes the calculation easier. And so I let the waters react and hydrolyze each other. But the population can't grow big because, you know, as the hydroxide concentration goes up, there's plenty of hydronium there to attack it. And so this is continually attacking the hydroxide, keeping the population very small, so that at equilibrium we're going to have 0.100 plus X molar and X molar here. Now I'm going to solve that for X. The Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. And so this is going to be 0.100 plus X times X here. This has got to equal 1.0 times 10 to the negative 14. Even though this is not that hard to solve, I'm going to use the simplifying assumption. If I use the simplifying assumption, X is much smaller than 0.100, then 0.100 simplifies, 0.100 plus X simplifies into 0.100. This is times X. And then, therefore, X is equal to 1.0 times 10 to the minus 13. Do you see? Here, they were mistaken. You know, they're saying the population of hydronium and hydroxide is going to grow all the way to 10 to the minus 7. But according to my calculation here, it can't grow that big. The maximum additional hydronium I'm going to get and additional hydroxide is 10 to the minus 13, not 10 to the minus 7. Many, many orders of magnitude smaller. But let's check our answer just to make sure. And so this is going to be 0.100 plus X, so plus point. Now I need 12 zeros and then a 1. So I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then a 1. Should do it. And so this is going to give me 0.100 sub 0.00000000001 molar. And then over here, the X value here is going to be 1.0 times 10 to the minus 13 molar. Okay, actually a couple of things I forgot to do. One is to justify my assumption. Was the assumption okay? So let's calculate the percent change here. The percent change is 10 to the minus 13 over 10 to the minus 1 times 10 squared. So that gives us 10 to the minus 12. This gives us a 10 to the minus 10% change. A 10 to the minus 10% change is extremely small, much, much smaller than 5%. And so the simplifying assumption is no problem. In fact, with a percent change this small, we would have gotten the exact same answer using the quadratic without assumption. The simplifying assumption is no problem here. It worked very well. We can do a double check of our K. You know, when we check our K value, the K comes out to 1.00 times 10 to the minus 14. So it checks out. And so this looks good. So we did this, and this is what we got, except we did this stepwise. And so how do I know if stepwise fails or if it was successful? The way I can tell is if step 2 perturbs step 1. So this was wrong. All right, so let me just add that here, down here. Stepwise fails if any step perturbs the previous step. Okay, so what happened here was, take a look. In step 2, I generated additional hydronium. If I generate additional hydronium, then both step 1 and step 2 are in the same beaker. That means that if step 2 increased the hydronium here, then let's go back to step 1. What does Le Chatelier's principle say? If I increase the concentration of the product, it should shift left. So I increase the concentration of the product, which means that it shifts left. That means I have to correct step 1 for that Le Chatelier's shift. But in this case, I don't have to worry about it because of one. Whenever we have a K that's very large, this is a one-way reaction. This is not perturbed by Le Chatelier's principle. So what I could do is I could double it. For example, if I went from 0.100 to 0.200, it's not going to shift. Because K is very large, it tells me it's only going to flow to the right. It's not going to flow backwards. And so here, even if I double it and went to 0.200, it doesn't perturb. And so if step 1 consists of strong acid, then I never have to worry about it being perturbed because it's always going to go forward because of the K value. It's very large. And so it's a one-way reaction, not perturbed. The other reason I don't have to worry about it is how much did I increase the concentration by? You know, I started off with 100 and then I added this much. Was that a significant change? No. And so the second reason I don't have to worry about this perturbing is because it was an insignificant change. And so in both cases, you know, I didn't have to worry. This is an insignificant change. Even if it was a significant change, I still wouldn't have to worry because I know that K is very large in step 1 and it won't be perturbed. So, you know, I could have went from 0.1 molar to 1 molar, 10-fold increase in concentration, still nothing would happen. But here, you know, heck, this is going from 0.1 to 0.1, you know, 0.001. So barely anything changed. So it's insignificant or negligible change, which means it won't perturb step 1 either. And so just to summarize, if we're looking at the inventory, if I have, let's say, a beaker that's listed here, 0.100 molar HCl, you know, that's what the beaker is. Am I going to find any HCl molecules? HCl molecules? No. I don't expect, all the molecules should have broken apart, right? Ionized or hydrolyzed. And so instead, what I'm going to find is this. So let's go down the list. I'm going to find chloride. What's the concentration of chloride? It's going to be, chloride's going to be 0.100 molar. And then this 0.100, I don't want to double count because this 0.100 went down to the next step here. And so it's still there. The 0.100's here, and then we're adding a little bit to it. And so this is the final amount of hydronium. So the hydronium is equal to 0.100 sub 0.000000001 molar. 9 zeros. Is that 9? After? 1, 2, 3, yeah. And then I have hydroxide. The concentration of hydroxide shown here. And the hydroxide is 1.0 times 10 to the minus 13 molar. And so that's the inventory. And then let's calculate the pH of this solution. The pH is going to equal the negative log of the hydronium ion concentration. What does it come out to? We're allowed 3 sig figs. Is that 3 sig figs or 4 sig figs? actually, this is a power function, so this is 3 sig figs. It's after the decimal. This here is 3 sig figs. So 3 sig figs, 3 sig figs. A pH of 1, is that acidic or basic? Yeah, it's very acidic. As you'd expect, you know, it's strong acid. And so you'd expect it to be acidic. But there's something weird. What's strong base doing here? If I have strong acid, shouldn't the strong base neutralize that? Or if I have lots of strong acid, that strong acid should neutralize all the strong base. And so if I have some hydroxide, well, that's a perfect reaction. Hydronium plus hydroxide yields water. So why isn't the hydroxide down to 0? Is it possible to bring the hydroxide down to 0 because this is a strongly acidic solution? Yeah, the problem is you can never get rid of it. The water is going to, you can't stop the waters from colliding, and the waters are going to continue to collide to produce that hydroxide. So yeah, the hydronium will attack that hydroxide. That's why the population is so small. Hydronium is the predator, hydroxide is the prey. And so it attacks it, but it keeps reforming. And then it gets attacked again, and eventually it will reach the state of dynamic equilibrium where we'll just have a stable population, you know, predator-prey. And so that means this, as far as defining an acid goes. As far as defining acid goes, acid solution is going to have a hydronium ion concentration greater than the hydroxide ion concentration. Neutral will be equal, and base will have a hydroxide ion concentration greater than the hydronium ion concentration. All right, so the next example is going to be 1.0 times 10 to the minus 8 molar HCl. So why don't you do this? One, and then figure out the pH. All right, let me interrupt you for a second there. All right, if you're interested in the pH, then you're thinking, I don't want to do all that work, this multiple equilibria type stuff. Because did you guys do pH calculations in intro chem? Weren't they a lot easier? So for example, this Chem 4 style, if we had 0.100 molar HCl, then we automatically said we have 0.100 molar hydronium, which means we have a pH of 1.000. All right, wasn't that just a lot easier? But therefore, a 1.0 times 10 to the minus 8 molar HCl solution should give us 1.0 times 10 to the minus 8 molar hydronium, which should result in a pH of what? Maybe I should back up. Let's talk about pH then. Give you some examples here of pH. Let's look at the hydronium ion concentration, the hydroxide ion concentration, and pH. If the hydronium ion concentration is 1.0 times 10 to the minus 7 molar, and hydroxide is 1.0 times 10 to the minus 7 molar, then the pH is 7.00. The pH is equal to the negative log of the hydronium ion concentration, or it's just the power, the negative power of the hydronium, which is 7. For acid solutions, it can go up. Let's say I'm at 1.0 times 10 to the minus 3. If I'm at 1.0 times 10 to the minus 3, then the two exponents have to add up to negative 14 because of Kw. So that means the hydroxide must be 1.0 times 10 to the negative 11. 11 and 3 gives us 14. And therefore the pH is the power, the negative power of that's 3, and then I need 2 sig figs, 3.00. Let's go on here. I'm going to go up. Let's go to, if I have 1.0 times 10 to the, let's go to 1.0 times 10 to the 0 molar. Then this must be 1.0 times 10 to the negative 14 molar, and the pH is 0. And so if I'm at 1 molar, pH should be 0. The first thing that's going to be different than Chem 4 is this. In Chem 4, did you have any pHs below 0? Any negative pHs? Well, let's say if you had 6 molar. Can you make 6 molar HCl? Is it possible to make that?
Yeah.
So if we have 6 molar here, then what is the pH? It would be the negative log of 6. What is the negative log of 6? Negative 0.77. Is that possible to have a negative pH? Yes or no? Yes. A lot of people say no, it's not possible to have a negative pH. A lot of people say the pH ranges from 0 to 14. Is that true or false? pHs range from 0 to 14. True or false? False. The pHs go beyond 0 and beyond 14. And so why do a lot of people think that pHs stop at 0 and 14? Why? Because there were no problems. You never did a calculation where you had a negative pH, right? And you never did a calculation beyond 14. And so why is that? That was on purpose. They purposely left out those calculations. Do you know why? They purposely left out those calculations because they didn't want to screw things up. You know, the calculations work quite well. The calculations work pretty well from 0 to 14 because the concentrations are fairly low. But when you start getting into high concentrations, the calculations are off. You know, there's a more significant error associated with those calculations because you shouldn't be using what they call the stoichiometric or the ideal concentration. You should be using the effective concentration or activity, because at high concentrations, what becomes a problem? Yeah, interionic attractions, ion attractions. And so, do you remember, sodium chloride should split up ideally into two particles, sodium and chloride. But at higher and higher concentrations, it doesn't split up into two particles. It splits up into less than two particles. Do you guys remember the table in chapter 13 at the end? Yeah. And so what happens is, we can't use these ideal concentrations. Yes, it says 6 molar on the bottle, but really, what is the hydronium ion concentration in there? The effective concentration of that, right? The activity. And so, this is why, like in Chem 4 or Intro Chem, they'll try to restrict you between 0 and 14, so we don't have to worry about these deviations, from ideal behavior. But in Chem 1B, no, we don't want to restrict ourselves necessarily, but we aren't going to go into the proper, calculation. All we're going to say is that, when the pHs get below 0, then, there's more uncertainty associated with those because we shouldn't be treating those ideally. And when the pHs go above 14, the same thing, Yes, they can go below and above, but calculations aren't going to be as accurate. So that's the first thing from Chem 4, because that's not really discussed. The second thing from Chem 4 is they never told you you're dealing with multiple equilibria and pH calculations. All they did was, okay, if we have 0.100 molar HCl, that gives us 0.100 molar hydronium, which gives us a pH of 1.00. If we have 1.0 times 10 to the minus 8 molar HCl, then we have 1.0 times 10 to the minus 8 molar hydronium, which gives us a pH of, well, the pH is a power function. It's a negative power. The power is 8, so this gives us a pH of 8.00. We are allowed 2 sig figs, so this is 2 sig figs. This is going to give us 2 sig figs here. So this is a typical Chem 4 calculation. You think, hey, that's a lot easier, right? I've done these pH calculations. They aren't that hard. They're easy. But there's... that was pretty easy. That was easier than doing what we just did. If we did the HCl problem again, here, we got the exact same answer. Isn't that the same answer we got earlier? It's the exact same answer, and just a heck of a lot less work. But there's something wrong with this calculation. What's wrong with this calculation? This is what's wrong. When the pH is 7, we call this neutral. When the pH is less than 7, we call this acidic because it has more hydronium. And this is the hydronium here. Then hydroxide. And so pHs less than 7 are acidic. pHs greater than 7 are basic. And so a 1.0 times 10 to the minus 8 molar solution of strong acid is actually basic. Is not acidic, but it's really basic. Is that true? This is basic. This is strong acid. Hey, wait a minute, isn't there hydroxide, strong base present? So maybe the strong base is what's causing this to be basic. Is that true? And so this is wrong. And so in Chem 4, you would have never been given this kind of problem because you would have automatically gotten the wrong answer. They don't want to throw the wrong answer at you. But did they ever tell you that we're dealing with multiple? No, they never told you that because it's too much work, too complicated. And so the easiest thing to do is omit problems like this. If you omit problems like this, you'll never have any trouble. Just like if you omit negative pHs, then you never have to talk about them, or pH is greater than 14. You never have to talk about them. If you never have to talk about them, then don't worry about them. But the problem is solutions don't care if you know how to do the math or not. And so just because we artificially restricted the type of problem doesn't mean that those are the only types of problems you're going to encounter. You're going to encounter all kinds of problems. And so this method fails. And so this is why I did so much work. 0.100 molar HCl is a pretty simple calculation, but it was a lot of work. Well, the same thing with this. So continue this one, just doing it the way we did it, or you did it, for the HCl. This is wrong. Chem 4, we automatically assume Kw can be ignored. In Chem 1b, we can't assume Kw can be ignored. Wrong to dismiss Kw. And so why don't you do the calculation? Unless, did somebody already do the calculation?